the reason why we're here, obviously, is for iMachining. I'd like to take the time to show you the technology behind iMachining and show you how different this particular product is from a lot of the other things that you may or may not have seen out there on the market. iMachining is a patented technology. We have a tenured professor who has just done absolutely incredible things with this particular application. It's been in development for 5 years or so, Ken, is that correct? Read about 5 years?
Yeah, almost 6.
6 years? And
it's pretty close to 6 now.
Absolutely, absolutely. So, so with all that being said, again, I mentioned this to some other people. For those of you who just joined us, there is a questions tab or a questions pane in the go-to webinar section there. And if you have any questions along the way during the presentation, please feel free to type in the question into the pane. We're going to be monitoring those throughout the presentation, and we'll do our best to get to those during the presentation. But if we don't, at the end of the presentation, we'll go ahead and address everybody's question individually. So please feel free to ask the questions. So with all that being said, I think what I'm going to do is I'm going to turn this over to Ken Merritt. Ken will kind of get us started here, and but we'll all be here to make comments and things throughout the presentation. So Ken, if you will.
You betcha. All right, guys. Well, again, thank you for joining us, and let's just kind of dive right into this. We're here for what? To see a little bit about iMachining, and what we want to talk about to start off with is the iMachining Wizard, because this is one of the things that really brings a whole nother level to SolidCAM's iMachining product than what you're going to see elsewhere. And I'm going to get into a little bit of the technical stuff on it later on when I do some software application of it. But to start off with, Brendan, you've talked to several of our customers up there in your area that are using it. Can you give us kind of just a quick, not real deep, but a quick customer perspective on what the benefit is of this wizard?
Yeah, you know, that's a great question, Ken. A lot of what the feedback that I get from my customers, in fact, I've got a guy who's he's in like Western New York, calls me about every 2 weeks just to tell me how much he loves the iMachining Wizard, and it's really fun to hear that kind of feedback, because you know, really, he just tells me all the time it just makes his life so much easier. Because of the fact that there is so much technology in this particular product, but he tells me all the time, he's like, oh geez, this is great, this one window, I just go in, I make a few different selections, and I'm off and running. So you know, really, again, that whole ease of use thing just really comes into play, and he's just super excited about it, and it's not just him. You know, I've got, every time we do presentations, people always look at this wizard and they go, how can it be this easy? There's got to be some sort of trick to this. And you know, and as Ken's going to show you as we move forward, the amount of technology that's behind this is incredible. But this is really where the you know, where the rubber hits the road, because all of the, you know, this one particular screen right here is the only thing that you need to make iMachining work, and it's really truly amazing technology. So and really, it kind of brings it out of the gate as installed. You know, level 1, 2, or 3, you can definitely get a first run success cut, and then ramp it all the way up to 8 if you want to start getting a little bit more aggressive. But let's go ahead and get started here and talk about what we're going to be doing. This is the part we're going to be cutting today, and I'm going to go ahead and start up the camera inside the machine, and you guys should be seeing that now. Yeah, and Ken, as you're doing that, as you're getting the machine ready to go, if for everybody that's looking at the screen right now, you can see that there's a bar, like a separation bar between the live image of the spindle of the machine and the PowerPoint. So what you can actually do is you can sort of slide that over. If you hover over that, you can maximize or make the image, the live camera image, a little bit bigger. So if you just kind of click on the separation pane and then drag it over and maximize that, you'll be able to see a much larger image. And as you can hear, we're adjusting the
Sorry, I got my head inside the machine here for a moment.
That's okay. And so we're going to go ahead and get started with what everybody came here to see today. And
Okay.
Ken, why don't you, if you can just sort of narrate what's going on there.
Yeah, absolutely. Let me kind of fill you in on what's going on here. This is a 1/4-inch diameter tool. This is a 3-fluter. We're working with a 3x5 block of steel, 1 inch deep. And we're going to be cutting at 625 thousandths depth of cut. The steel grade in this is 1018 cold roll. And I think you're going to be fairly well impressed with what we're about to do here. So let's just go ahead and get it started, and then I'll tell you what's going on. All right. Now, iMachining does support pre-drill locations. So you can pop some holes in here and then come right in and start cutting. But in this presentation, I also like to show you that we can just helix right into the material. Very, very good control over the helix. We have independent control on the spindle and the feed rate for the helix versus the rest of the cut. Now that we're down at 625 thousandths depth of cut, we're now cutting at 10,000 RPM and between 90 and 100 and looks like 165 or thereabouts inches per minute. And the reason that's a variable feed rate is because we're using what's called a morphing spiral. Now, a morphing spiral is very interesting in that we can run between a range of minimum cutting angle and maximum cutting angle so that the spiral can actually change shape as it grows. And it can move from one shape to another without ever leaving the material. As you saw there, we did quite a bit of cutting without the tool having to be repositioned. When that is changing the angle like that, when it's at the maximum angle, we're running at the programmed feed rate in the wizard. But as the cutting angle comes down to afford the morphing, we actually increase the feed rate so that we sustain a constant chip thickness at the angle of contact. And that's one of the things that's very different about how we're programming ours versus some of the other systems that may look similar to this on the market. Almost everybody else that I know of, I don't know of anybody doing it our way, is working with chip load. In other words, the thickness of the chip at the 90-degree quadrant relative to the direction that the tool is traveling. We're actually working with the chip thickness at the contact point where the tool is actually cutting. Okay? The motion you're seeing right now is what we call a D-slot tricoidal. And this allows us to very quickly reposition the tool and then take another cut in this managed cutting angle methodology. Now, by the way, the spindle load meter while we're doing this is virtually negligible. It's not even really picking the meter up off the bottom. So you can see it's a very, very light cut, and yet we're removing a lot of material very, very quickly. Okay? Also notice that reposition move that you just saw in there was down inside the pocket. One of the things that we've put an extensive amount of effort into is optimizing the repositioning moves. With our 3D iMachining, every movement of the tool is also updating the remaining stock qualification. So we have this constant stock update that we use, and for each movement of the tool, this is actually during runtime of the algorithm, we're recomputing where that remaining stock is so that we know exactly where we can safely move the tool. And that way we don't necessarily have to return to the rapid clearance plane all the time, which can be a little bit of a hindrance. Now, you may not really think about this too much, but every machine, when it switches from G1 to G0 and from G0 back to G1, is going to pause for a moment. Well, if you do that 1,000 times over a particular cycle, you've added quite a bit of time to your cut cycle. Okay? Now, what you're noticing going on here is what we call the step-up staircasing. And this allows us to actually create the 3D shape to a very near-net scallop height calculated by the system. We simply tell the system what scallop we want at the end of this, and it's going to take care of that regardless of the angle of the walls. And so you can see very quickly we're removing all of the shape inside this cavity and preparing it for the finishing tool. Now, one of the things that's very, very important about this, the consistency of that scallop carries a lot more importance than a lot of people want to admit, and that is when we go to the finishing tool, one of the things that causes us to have to do what they call a semi-finished tool path is that if the roughing path leaves an inconsistent staircase, then our finish tool would see uneven loading and unloading during its cut time. This would obviously cause issues with our surface finish. As you're going to see at the end of this cut, we're not going to do a semi-finish on this. We're just going to go straight to the ball tools, and you're going to see a very, very nice surface finish at the conclusion of this operation. So what we're doing again now is staircasing, and it's doing a little bit of flat leveling in some shelf areas, but notice that we start at the bottom and we work our way up to the top so that we can take advantage of the work that we've already done at the deeper cuts. And this optimizes the amount of material removal within a specific amount of time.
Hey, Ken, I think it's also worth noting here, too, as we're looking at the way in which the machine is actually cutting this material out. You always notice, too, that, and again, I think maybe you can expand on this a little bit, is the tool itself is always remaining at its current cut level. You don't see a lot of those retract moves and, you know, wrap it up position, wrap it back down. And that's part of the detour move. Is that correct, Ken?
Yes, it is. Yeah, and that's kind of what I was explaining a bit ago about the repositioning moves. The way we can do that is what Brendan is talking about. We have a function called detour moves, and the user actually has control over this. You can specify the distance of a move that you want to be within the retract or within the detour. Okay, and so if the move distance exceeds the value that you set in the interface, then it'll go ahead and jump up to the rapid clearance plane and do a standard G0 movement. Now what you're seeing here is a very narrow slot using the D-slot for coil style movement, which we were able to clear that very, very quickly without, again, having to overload that tool. And what we're going to talk about in a few minutes here, we're going to get back into our PowerPoint presentation as we let this go through the finishing operations. And we're going to discuss a lot of the physics of what you're seeing happen here and how it works and why we're able to move so aggressively through steel without damaging the tool. And as you can see here, we are just about finished the roughing operation, okay? And we're going to go into the flat floor finish in just a moment. And then, of course, it's going to bring out the ball tool and start doing all the surface finish cuts on this, and you're going to see some pretty cool stuff. And I want to talk just a little bit about the machine that we're on, and I'll kind of get into a little bit of that later on, but this is a Herco VMX 42 HSI, and we'll kind of show you a picture of that a little bit and talk a little bit about what's going on there. We really try to maintain machine neutrality. We try not to really support one machine over another. Some of us have our own personal opinions, and for myself, I've been fortunate enough here to work with these guys for a couple of years now, and I'm really starting to kind of like these Hercos. They're pretty nice machines. But as this is doing the flat floor finish, why don't we go ahead and go back into the PowerPoint presentation. So if you would, slide that slider bar back over and kind of minimize the size of that camera. And let's go back into the PowerPoint and begin talking a little bit about what makes this science work, okay? So the question is, you know, well, what is iMachining? That was a very strange-looking toolpath, the way it approached that cut. So what is it really? And what we're doing is we're managing the science of cutting angle, which is a different way of looking at the tool and material engagement, okay, and how we control that. Now, one of the things that comes to mind that we really need to discuss is the fact that we're not really cutting when we're talking about machining metal. This video here is a very, very magnified view of a chip being removed on a lathe, okay, and this is the way they can do it, is by doing this on a lathe. Very high-speed video and very magnified, but this is about a 2.5 to 3 thousandths thick chip that's being removed. Let me just go ahead and put that into repeat and let it just keep going there. but you can kind of see where the material is bending underneath here and coming back up. That would be known as elastic deformation. What's happening up here on top, the chiseling effect that you're seeing here, is what we call plastic deformation. And that is where we're deforming the molecular structure beyond a level where it could return to its natural state. Okay? So I want you to kind of keep this in mind as we begin going through and talking a little bit more about some of the various different physics aspects of what's going on. One of the things that is paramount as we talk about the kind of cutting that we're doing here is the cutting edge velocity. And I want you to think about something. If you take a sharp knife and put it on top of a tomato and push it straight down, it will cut the tomato, but it's going to squish the tomato on the way down, right? If you take that same sharp knife, put it on that tomato, and you drag it real fast across the top of the tomato, the knife will virtually fall through the tomato without any effort whatsoever. The reason for that is because of the increased velocity on the cutting edge. Makes the energy necessary to make the cut a lot less. Same thing applies in the physics of what we're doing. As we increase the cutting edge velocity, it's not really a linear inverse relationship or anything, but we reduce what I call the latent energy of plastic deformation. And that is the energy that is necessary to initiate and to sustain that plastic deformation function that removes the chip. Okay? Now, a couple of things happen in relationship to the pressure vector on the flute and where it is aligned based on what angles we're using to cut. And I want to kind of talk a little bit about that. When we're in a proper alignment, where the tool is over here on the right-hand side of the cut, we have rotational velocity on the tool this way. We have forward velocity on the tool this way. When those two are in balance and the cut is less than 90 degrees, then we have a pressure vector that is aligned something similar to what you're seeing right here. Okay? Now with the grind of the tool, this internal concave grind here is designed for several reasons. Number one, to curl the chip and eject it. But also number two, it's kind of the area where we dissipate some of that energy based on the direction of the pressure vector. The outside curve, the convex out here, is for the strength in the flute. And that kind of takes the pressure that is being applied along this vector and reroutes it back into the core of the tool. Okay? So when all of this is in balance, what we wind up with is we have a tool that is running very, very stable and with a very stable pressure vector and managing that energy that is being applied to that tool very effectively. Now, what happens over here on this side is a little bit different, okay? When we get into a traditional style of toolpath pattern where it's just an offset toolpath, you'll notice they have these sharp direction changes throughout the entire operation. I like to call these compression zones. They're kind of an area where we wind up overloading the tool and creating very negative forces on the tool. In these conditions, we wind up seeing the tool in what we call a full width of cut. Now when the flute is on this side and it's advancing through this cut, you can see by the red here that we're getting a chip thickening condition, which means that that energy of plastic deformation is actually going up because the chip is getting thicker and thicker and thicker as the flute advances through the cut. We're also adding rotational velocity to forward velocity here, so we've actually got a little bit more velocity on the tool than what we think we have. Another thing that's happening over here is that this pressure vector, when the flute is over in this zone here, and as it starts to approach up in here, the pressure vector is really pushing almost in direct opposition to the direction that the tool is traveling. That's going to create a linear force on the tool, which is kind of a deflective force, if you will. In this condition up here, really all we have is rotational or torsional forces on the tool. We don't really have any linear forces where we're pushing the tool against what it's cutting. Okay? Another thing that happens over here is as the flute is advancing through this left side of the cut, the chip is actually being curled into the direction that the tool is traveling. This creates a condition known as compaction. When we have compaction, we also get a phenomenon known as conduction of heat into the tool. So all the work, the heat of work that is going on with removing that chip through that function of plastic deformation generally is being tossed off with the chip. But if we compact the chip into the ejection galley, then we're transforming or transmitting that heat into the tool through conduction. Now, over the years, that's really kind of been the limiting factor for us. Notice that when you look at the feeds and speeds recommendations by most of the tooling manufacturers, they're fairly low, okay? 260 to 300, maybe 350. You might see some people advising up around 450 or 500 surface foot, but very rarely, okay, in steel. And the reason being is because in that full slotting mode, we're going to overheat that tool, and we'll break down the condition of that tool and cause it to fail. Also, because of that pressure that's being applied in a linear fashion, we've never really been able to cut very deep with a tool because that pressure goes up exponentially with the depth of cut, with the increase in depth of cut. And that's why we wind up breaking tools off all the time. So we're doing several things, very, very different in what we're doing here. Now, there's also a phenomenon that occurs right here at the 90-degree quadrant, okay? And that is that as this flute passes the 90-degree quadrant, for just an instant in time, when the flute is exactly at 90 degrees, the effective rotational velocity suddenly becomes 0. And yet we still have forward velocity on the tool, and therefore this pressure vector suddenly flips to the outside and is pushing inward on this flute instead of where the flute is designed to carry that pressure. Now, that creates what we call a pressure vector oscillation, and it creates a vibrational shock known as harmonic vibration. What's the worst thing you can do to carbide? Is shock it. Whether we're talking about impact shock, whether we're talking about thermal shock, or whether we're talking about vibrational shock, the worst thing you can do to a carbide substrate is shock it. And that will cause it to fracture because carbide is very hard, which is what allows us to cut better with it, but it's also, as a function of that hardness, it's very brittle, okay? And so we want to kind of keep those things in mind as we're going forward. Now, we talked about the cutting angles, okay? Our algorithm has a minimum of 10 degrees and a maximum of 80 degrees. And I want to talk a little bit about why that is so you kind of understand why we made some of the decisions that we made. In our practical experience, we've discovered through monitoring conditions on the machine and listening to it and evaluating the tool afterwards and so forth, that somewhere between 85 and 90 degrees, and that depends on the ratio of rotational velocity to forward velocity, we begin to see the pressure vector start to swing to the outside. And it never really fully reverses until exactly at 90 degrees, but it will start to swing above 85, okay? Below 80, we don't really notice any of that. And so we looked at the efficiency of the tool path between 80 and 85 degrees and realized that it's pretty negligible, okay? So it didn't make any sense to push it up to that limit. We went ahead and kept it down below 80. Most of the time that I'm cutting, I'm running 65 or below, okay? 60 is where I kind of like to run things in soft steel. If I get into some really hard steels, I'll roll it down to 35, 40 degrees if necessary. But that's kind of why the maximum angle is set where it is. We don't ever want the tool to get close to this point where that vector flips because that creates the instability in the tool. The 10 degrees is kind of interesting because, number one, anything lower than 10 degrees is pretty inefficient. We're just not taking off any material. But number two, remember that video we showed at the very beginning. In order for that plastic deformation to happen, we have to get the flute underneath the material and get that chiseling action going, okay? Less than 10 degrees, we stand a very huge chance of just bouncing that tool off the top of the material, which would then burnish the edge and essentially dull the tool. So that's not a good thing either. Now, in general, I usually run somewhere between 15 and 20 degrees as my minimum just to keep the efficiency of the tool path up a little bit better, okay? And we'll kind of go into some of that as we talk about some of the other things going on when we look at the software. Now, some of the problems that we have with traditional pockets include the fact that a traditional pocket is basically a parallel offset, like I was discussing earlier, okay? And so we have lots and lots of these compression zones all over the toolpath where we create that overloading of the tool. Because of those linear deflective forces, our depth of cut has been restricted, and we don't get to use the rest of the tool. And we've also had to kind of keep the speed of the cut at the lowest common denominator. It's cutting all of this stuff out here at the rate that it can manage these compression zones. Okay, so not really an effective toolpath pattern. For years, we did things like standard trochoidal, which basically just orbits the tool at feed rate into these corners, which does mitigate the issue a little bit. Okay, it allows you to run a little bit faster, but really all it's doing is it's oscillating the duration of those negative influences on the tool. We're still overloading the tool. We're just doing it for quick, short moments so that we don't get a sustained overload. Okay, and so this kind of worked. It was better than nothing, but it really wasn't the right way to solve the problem. So what is iMachining? Well, iMachining is a very complex tool motion algorithm that completely changes the direction that the tool runs, okay? And as you can see, there are several technologies that we're using that allow us to take a completely different approach to how this tool path is managed.
Hey, Ken?
Yes, sir.
For those of us who don't speak Klingon and aren't used to your big 16-cylinder words, can you can you maybe talk a little bit more about the like the separation channels and morphing spiral, and maybe even perhaps volume mill, true mill,
Okay,
dynamic
sure.
mill, that kind of thing?
Yeah, no problem. No problem. Klingon, give me a break. Boy, I tell you, the things you got to put up with these days. Now, really what's going on here, the D-slot trochoidal is the motion that you're seeing in here. Now let's kind of walk through a cut here and watch what it does. This is the center line of the tool right here. So as the tool is passing through here, we'll notice that when it comes to the end of this cut, it actually does a helical move here, comes up off the floor just a little bit, and then this is a G1 high feed rate repositioning move. And it comes back over here and comes back down in for the next cut. And hey, just a quickie, let me point you over to the camera inside the machine right now. That's an 1/8" ball tool, guys. We're doing the final clean out in the rest material down in the bottom of these pockets, the little bitty fillets in there. This is running at 16,000 RPM and 160 inches a minute, dry in steel with an 1/8" 2-flute ball. And you're going to be amazed at what you see for a surface finish in there. It's crazy, okay? Also, I wish you could feel this machine. This thing is like dead smooth right now. Even running that fast and changing direction as rapidly as it is, the machine is running extremely smooth. Very, very nice. So I just wanted to point that out because we're getting close to the end of this cut here. Anyway, back to what we're talking about here. So that kind of explains a little bit about the D-slot trochoidal and how it works. It just oscillates through here and continually cleans us out without ever overloading the tool, and also with a very effective repositioning move instead of going feed rate all the way around the circle, okay? The morphing spiral is this guy in here, and what that allows us to do is that allows us to keep the tool in contact. So you're not making any money on the machine if the tool's repositioning. It's a necessary evil, and we have to do it sometimes, but the more we can keep the tool in contact with the material, the more chips we're bringing off of it, okay? And in order to get from some abstract shape like this down to a collapse center, we can't keep it at a solid single cutting angle. We have to allow it to morph between a minimum and a maximum in order for it to be able to stage through these areas. Now, again, we've kind of exaggerated this. We're showing some real thin areas here and some fairly thick areas here. Not necessarily exactly how I would want to do it for production, but it does do a very, very good job of keeping the tool in contact and letting it change the shape into another shape, okay? But in order to facilitate that, we have to use what we call separation channels, okay? Now, also make you aware that there's several parameters in the software that allow us to control these features as well, because every model that we're going to be cutting is going to wind up with some different geometry shapes in it, and we may have to manage things a little bit differently from one part to the next. So we give you that kind of control over it so you can kind of keep the efficiency up as high as possible. But the idea behind this separation channel is to clear this area from the rest of the part, which would leave this block standing, and then we can move from the outside towards the inside on this and never again run into an internal corner, which makes it much easier to manage the over-engagement, okay? It's kind of a weird thing going on here, too, that I want to talk about, and that is that if we just took a single separation channel out here at the same width, we'd wind up leaving a thin wall out here, and we'd have to manage that thin wall by coming out here and cutting it down one way or another, either with a morphing spiral or with offset D-slots or whatever. But because it's so thin, and because the goal of this is to go deep, we could wind up bending that wall over, which would, of course, cause tool breakage. And so we want to avoid that, so there's what we call a thin wall thickness parameter that the user has control over. And if, during this channel separation mode, if it sees that it would leave a wall thinner than what the parameter is set to, then it'll just go ahead and morph the channel out, take that wall out on the way, so that we don't have to deal with it later. Okay? Kind of a cool little feature. Now, in talking a little bit about separation channels, there's also some things that we need to pay attention to. You know, theoretically, we could just separate this along here and not do any of this here and just morph this entire area, but that would create a real inefficient tool path. That would create a tool path that did a lot of long cuts at or very near the minimum cutting angle, and would do a couple of short cuts across here at or very near the maximum angle. That wouldn't be very efficient. And so what we did is we created a separation efficiency parameter that allows the algorithm to actually evaluate the topology of the model and go in here and break it up into more symmetrical zones where we can keep the tool closer to its maximum cutting angle, where we're going to get the most efficient tool path. And so we kind of handle some of these things that some of the other systems out there you were talking about, volume mill and dynamic mill and SolidCAM's true mill and some of the other ones that do things similar to this, they don't have any of this technology. This is all patented technology. And so when they look at a morphing spiral, they see it as very inefficient, because a lot of times what we're showing is an exaggerated picture to kind of get the idea across. Not really what we would be doing. We'd be doing something more like this, where we'd split it off into equal zones and remove it very efficiently. And so some of these patented technologies are very, very powerful compared to some of the other things that are out there on the market today. Let's kind of walk through a typical part here. Whenever we can, we're going to focus on that morphing spiral, because again, the tool is in contact the whole time. You're removing chips, you're making money, right? Now, when we run into islands, we have to do something. So we have to, we have to separate them correctly or do whatever we need to do. We'll use the D-slot trochoidal for doing that. There is repositioning going on in that, so it is less efficient than the morphing spiral. But if we can return to a morphing spiral, we will, because again, it's going to increase the efficiency of that metal removal rate. Deal with what we have to deal with, but even if it's just for a very short period of time, we're going to try to return back to that morphing spiral whenever we can. Now, within the confines of the shape of your model, you're going to reach a point where you have to finish the rest of it with the D-slot trochoidals, or what we call parallel offset passes. The thing is, our algorithm allows us to, again, use that minimum to maximum cutting angle, and so we can make that a much longer cut and reduce the amount of repositioning that is required to achieve the removal of that material. And, as I was talking about before, instead of always coming up to the rapid plane, coming back over here and coming back down, we create little detour moves in here, because we know the areas that are clear, and we just offset from any of the areas, and then we have a band of zone that we can move that tool in a G1 move without having to pick it up and run into those two pauses plus the distance of travel that you have to go in the rapid. So it makes it a much more efficient way of removing that material. Now, we also support, obviously, iRest, which allows us to use a larger diameter tool, come in, clear the areas out, but where that tool didn't fit, when we come back in on a rest, it'll just focus on that area and use the same iMachining technologies to pull those areas out. Okay, most of you probably know that rest machining comes from the RE in remaining and the ST in stock. Remaining stock removal is rest material. Now, finishing is a very interesting kind of a thing. You guys have all seen this, where the model radius is very near the size of the tool radius. And even on a finished pass with only 10,000ths on the wall, we come in here and we hit this wall and it chatters and chirps. Leaves those diagonal stripes coming up here, and not a good surface finish. A lot of times we have to go in, hand finish those areas and clean them up a little bit. iMachining's iFinishing process actually takes care of that, because it goes in and it evaluates these corners first. And if it sees that the area would over-engage the tool, then it'll go in and do the D-slot tricoidal to remove the amount of material that would cause the over-engagement without violating the minimum wall thickness or the minimum chip thickness, so that we don't wind up with that burnishing effect going on the tool either. And what that results in is, even with very, very near sizes on the radius in the tool, we can see a contiguous tool path go through here that does a very, very clean job of finishing that without chattering in these corners. Okay. Now, the machine is finished over here, so I want to go over and talk about something here before we go on into this next one. Number one, let me wheel this thing back out here. I'll go into manual mode, and let's pull this back out. Let me go ahead and readjust this camera too. Hang on a second. Let's get some of the chips off of there. Okay, I'm going to pull this guy out, drop it down a little bit so we can get the tool out of the way. And we'll just kind of dial that down. Okay, and let's get her into view. And we got her twisted just a little bit, but that'll be all right. Okay,
yeah, it doesn't look too bad there, Ken.
Yeah, it doesn't look too bad. Let's see if I can center it up just a little bit better. Okay.
Oh, there we go. That's perfect.
All right, now let me bring her down just a little tighter, make sure I miss the back of my vise with the tool back here. But that should get us down to where we're actually getting a pretty good picture of that. And what you can see in here, notice these fillets and stuff down here in the bottom and the walls over here. You can actually see the shine on that wall right there. And you can kind of see this is getting a little bit of light glare, so you can't really see this one terribly well. But this is probably the worst finish in here of all of these walls. And if I'm just doing kind of a thumbnail drag test along here, most of these walls I would say are easily within that 16 to 18 RA finish, especially these guys over here. They're really nice looking. The floor, easily 16 to 18. This area right here, I would say, I'm not really getting a scrape on the wall, not feeling a lot of vibration, so we're probably still 24 to 26 RA finish in that area. But what blows my mind is these fillets down here where that tool was running really, really fast. They're really nice. They're like even down in there tight, going long ways or going across it. I'm only seeing something in the neighborhood of, it's got to be real close to 16. I mean, it is super smooth. Now I'm going to reach over here on the end of the way covers here and just grab a batch of these chips that it threw off of there. And just go ahead and sprinkle a few in here. Try not to cut myself on them. Did that once. That wasn't real pretty. Oh, look,
yeah, you don't want to mess up that manicure, Ken.
Yeah, right. But as you can see from those chips, you can see a real consistency in the chips. Okay, and this is really important, because what this is our feed rate advance. As that angle is changing all the time, we're continuously moving the feed rate back and forth so that that chip thickness remains the same. What that does for you is that keeps a very, very constant load on the tool. So this tool is not seeing a lot of shock. It's not going in and out of corners, and it's not changing directions where because it's changing a direction, the angle suddenly rises up and creates more linear load on the tool. It's keeping a very, very consistent chip thickness. So all of those stresses and forces on the tool are staying very, very stable, so that carbide is going to last a whole lot longer. Okay? I hope that kind of makes sense for you.
Yeah, that does.
Do you think of anything I missed in there?
No, actually, that does make a lot of sense, Ken. Obviously, having, the whole point is, removing the heat of the cut through the chip, and that's why, that's why iMachining works so beautifully, with those particular, with this particular type of part. And Ken was actually just going to, he switched over the slide here on the main PowerPoint. One of the things that I think is really supremely important to talk about is, we were talking a little bit earlier about the type of machine that we're using here today, and we talked a little bit about the tooling, the fixturing and tool holders and that kind of thing. One of the things that we obviously want to try to get across is, you don't have to have a brand new, $250,000 high-speed CNC machining center to make iMachining work. In fact, it's quite the opposite. We really try to let people know that, we want to be able to take advantage of what you've already got. Obviously, you don't want to have to go out and make an investment in capital equipment in order to have your toolpath really be effective. Well, again, this is the great part about iMachining, is the fact that we can take what you've already got on your shop floor and we can make it at least 2 to 3 times more productive than what it's doing right now. And I know that sounds crazy. We
can go a lot more than that.
Exactly. And every time we talk about it, people just simply don't believe it. But yeah. I have customers that are using old, Bridgeport Boss 8s, and they are machining far more efficiently than they could have ever imagined.
Than they would, yeah, absolutely.
And this video that Ken's going to show right now is a perfect example of that, and Ken will give you all the details on this particular cut.
Yeah, again, like Brendan's trying to say there, we're really not in the mode of trying to sell you new machines and new equipment. That's the last thing we want to worry about. Some of us believe it's a pretty good idea. As you invest, you can really take advantage of the new technologies. But we want to first take advantage of what you have, let you make some money on that, capitalize what you're wanting to invest into. So this movie is, a very unimpressive video, quite honestly. This is one of our customers out in Colorado, and they called me out there to try to help them. They were trying to cut a pocket very similar to this in 1018. They were doing hot roll and cold roll both, but they went to cold roll because they were getting less hot spots in it. But this is a 1-inch deep pocket. This is a 3/8 inch diameter cutter that's going in here. This is an old Haas TM1 tool room mill. And I mean, when I say old, I'm not kidding. This thing's been rode hard and put away wet. I mean, it is in tough shape. It's only got a 4,500 RPM spindle, and the machine can only move at about 50 inches a minute before it starts hesitating. So it's not going to be a real fast and dynamic cut. Doing this pocket over here, we did it his style, and he was running on a 3/8 tool, 3-flute, okay, same high helix that I'm using here. He was running 2,200 RPM and 18 inches a minute, and he was doing it at 50,000 step down was all he could get it to do without breaking the tool or just shaking the machine to pieces, okay? And by the time he was done cutting this pocket, the bottom 50 thousandths of that tool was shot. I mean, it was done, okay? And it was kind of hard. We had to come in with a new tool to finish this because it was leaving a stripe along that wall where the wear was building up. The further he cut down, the more it wore that 50 thousandths, and the bigger that cut became, the bigger that step became. Well, as you can see over here, I'm all the way at the bottom. And again, not a real impressive video. Let me go ahead and advance this forward for you just a little bit. Notice how much of the pocket I've got cut now. Look at the beautiful color of the chips in here. And I wish you could hear this. It's just ridiculously stable. Okay, let's go ahead and go on up further. Let's take it a little further forward. You can see how much of the tool, or how much of the pocket I've got cut out of there. And again, we're right at the maximum range of what the machine can handle. I'm running 4,500 RPM and 50 inches a minute is my programmed speed. And so during chip thickening, it's trying to run a little bit faster than that, but it's just not getting the throughput on the machine to do that. We go over here. Look, we're almost done with this. Let's take this all the way over to this edge, and we're going to watch this. Look at the color of the chips in here. They're just beautiful, okay? And when this tool comes off, I don't know if you can see it over the web, but this is 7 minutes and 25 seconds. He was 2 hours and 20 minutes over here because he had to take 20 steps, 50 thousandths at a time, at 2200 RPM, 18 inches a minute. It took him almost 2.5 hours, 2 hours, 26 minutes to cut this pocket over here, and he destroyed the tool doing it. I just cut this pocket in 7 minutes, 25 seconds, and when we pulled this tool out and looked at it, I'm not kidding you, under I think it was a 3 or a 4X eye loop, you could not see that that tool was worn. There was not even scuffing of the coating on that tool. Now, to prove them out, I ran 3 more pockets on this bar with that same tool, each one of them in 7 minutes and 25 seconds, and at the end of that fourth, you still, if you really studied it hard, you could see some tiny scuff marks in the coating, but that tool was dead sharp. Now, I don't know how many it would have cut, because we didn't do any more than that. I proved the point to him. He loves it. He's running like crazy with iMachining now. But I suspect probably 15 to 20 parts without issue. I mean, at 4 pockets, it wasn't even noticeable that it had been worn. To the average individual without an eye loop, I would have challenged you to tell me that that wasn't a brand new tool. Okay.
Sure. You know,
so
and
I want you to kind of think about that.
Yeah, sorry to interrupt. No, I just wanted to. Sorry to interrupt you, Ken. But you know, again, this is really, this particular video right here speaks, I think, everything about iMachining. Yeah, I mean, because you know, it's not just a question of cycle time. I mean, the cycle time is phenomenal. Number one, I mean, that's across the board. That's fantastic. But again, number two, it means you're not reinvesting in capital equipment, which means there are no other associated costs. And then, you know, again, like Ken, like you were saying, I mean, having that ability to preserve tool life like that, I mean, that's
phenomenal. Yeah.
It's incredible. It's just amazing. The savings is not just cycle time. It's so much more than that.
Right, so much more than that. All right, so let's go ahead and go on to the next thing here. Now, what I want to do, I do want to give a little bit of a shout out here. We're trying to keep this away from being a sales presentation, guys. We wanted really to focus on the technical aspects and the science of what's going on. But, you know, Applied Machine Solutions is the Southeastern distributor here for Herco, and they've been nice enough to allow us to use their machines for a couple of years now. So I do want to give them kind of a shout out and let you know that if you're in this region, or even if you're not in this region and you're just looking for various different solutions in the industry, Skip's got a good team of people, and they've got a lot of networking going. I mean, they really have tied in with a lot of different things relative to the manufacturing industry. So if you're looking for a solution, whether it's grinding, heat treating, coolant, tools, fixture holding, anything like that, these guys are a pretty good solution for you. They can get you pointed in the right direction, and they can sell nationwide on virtually everything except the Herco machines. Okay, so I would advise, you know, write this information down, and if you're looking for a good network resource to check in with some people and kind of find some good solutions, Skip's got a lot of really talented people that he knows, and we can hook you up with the right people. This is the machine that we were just cutting on. The Ultimotion is a software that they put on their controller that smooths it out. I was talking a little bit about how smooth it was running during the finishing. I would suggest, and again, we try to stay machine neutral, but here's what I would say. If you're in the market for a new machine and you're looking at a lot of different ones, I would recommend you look at a lot of different ones, but I would definitely recommend you put this one in the list of ones you want to look at, because price for performance, I'm pretty impressed with it. Okay, and granted, there's a lot of other machines out there that are very good too. So again, I'm not trying to promote the Herco. I'm trying to say I would jump in and at least take a look at it. You guys make that decision on your own. Tooling that we were using today was from YG1 and from GW Schultz. Both of these manufacturers of tools I'm finding to be a good cost-benefit ratio. They're not hugely expensive tools, but they perform pretty well. Okay, they're not top of the line, but they're not bottom of the line either. Okay, we have a relationship with both of them. In fact, GW I've worked with GW for several years now. We've done some custom tooling and created some new designs that are pretty cool. I can't really get into too much discussion about that right now, but we got some stuff coming up in the next 6 months that's going to just be phenomenal, and some of it's based on tooling with GW. Tool holding I will get a little bit more specific about, okay? I've done a lot of cutting, and I've pulled a couple tools out. I've cut the vice jaws a few times, put some pretty nice finishes on them with iMachining, but when you start getting really aggressive, and some of the stuff I do, the two that you saw today weren't real super aggressive, but I do get into some really aggressive cutting when I'm testing some of the tools. We've got a new parabolic ejection cavity tool that we designed that ISCAR is grinding for us. I've done some testing on that where I've run a 10 millimeter tool at 14,000 RPM and 512 inches a minute in steel at 750 thousandths deep at 60 degrees cutting angle. It's just absolutely phenomenal to watch it cut. But I'll tell you what, the down forces on those tools at that aggressive a rate is unbelievable. You'll suck a tool out of even a heat shrink, okay? So you got to kind of look at this. If you're going to get aggressive with iMachining, I would recommend taking a look at some good tooling holders. Power grip system here from RegoFix is a real good system. If you're not going to get as aggressive as I'm talking about, I would recommend that you at least look at some seriously high quality ER systems or the milling chucks. Now I like Lindex Nickin, for instance, for milling chucks. They've got some really good ones. I've used Shunk, I've used Big, a couple of the others. Most of them are pretty decent. Stay away from the cheap ones. You get what you pay for, guys. I mean, bottom line, and pulling a tool out is going to cost you more in broken tool, broken setup, scrap part, and time than what it was worth to buy that tool holder, okay? So keep that in mind as you're doing that. Brendan, you want to talk a little bit about our website?
Yeah, I'd love to. In fact, this is one of the things that we really take a great amount of pride in is the fact that we have just tremendous customer testimonials regarding iMachining. And in fact, there are a few different things you can do. Obviously Ken's showing you right here just a little bit of a hyperlink right to our website. We just have tons and tons of customer testimonials regarding iMachining, great videos, customer comments, customer interviews, things like that. But beyond that, if you want to see something that's a little less, I guess, marketing driven, is just do a simple YouTube search. Just go on YouTube, search iMachining, and you will see hundreds of customer posted videos about iMachining.
Can I throw out a disclaimer here?
I was just going to say they are very colorful in terms of some of the language.
Yes, some of these are our customers that have gone out and literally they've run the first part in iMachining and they're like, oh my God, I call it the holy crap theory. They look at it and they're like, oh my God, and they grab their cell phone and they start videoing these things, and it's not real professional sometimes. So if language bothers you, be careful what you're seeing out there. But the cool part is that, like Brendan was starting to say, we don't have any control over these things. These are just customers that are super excited about what they're seeing.
Yeah, it's pretty fun to watch, and that's the part about it that really just makes me love my job so much. You just see the reaction from people when they start experimenting with iMachining. And I mean, there was one video up there, Ken. I'm not sure if you saw it. There was a guy who was actually clapping at the end of a cycle time.
I saw that. That was funny.
And I just thought it was great. So, but anyways, please, I invite each and every one of you to just go ahead and visit the website, take a look at some of the testimonials, and something. Even if you have questions, even if you're just maybe doing a little bit of research about iMachining, you can see that Ken here has got a slide, or he just had that up, in terms of our technical support. Again, we have gone to just endless lengths to make sure that we have the best technical support in the business. And so if you call in and you want to talk to one of our tech guys, 9 times out of 10 you're going to get a live body on the other end who is an actual machinist. Most of our guys, in fact, I think all of us, are all either programmers or machinists or a combination of both. And
well, everybody on the tech team is a machinist. They've
right.
all been at least 10 years on the floor.
Exactly. So, just go ahead and give us a call. I mean, if you have any questions about it, if you'd like to see something further on it, just call the support number. We'd be happy to talk to you and walk you through it. Very, very simple and easy. Absolutely.
All right, now I want to take you a little bit through the actual application itself. We've got just a few more minutes left here before we run out of time. Actually, we're coming up on a hard stop here shortly. But I wanted to show you something real quick. There's something really powerful. We talked about in the 3D iMachining, the way it does the scallop height. Now, I want you to kind of pay attention to this area right here and this area right here. We have two different angles of walls, and yet the step up is managed automatically by the system such that it creates the same scallop. And that kind of looks a little bit weird. When you look at this, you think, well, these got a lot bigger Z-step in it than these do, so wouldn't those be different? Let me show you what that looks like for reality. Let's go into the simulation on the next toolpath so that it'll do the automatic stock update for us. And let's take a look at what this does here. You can kind of see when you look at it from this angle, it looks like, yeah, this is much more coarse here than this is here. But when you roll this over and look at it from the side, look at how interesting that becomes. The actual angle or the actual distance of the step here is the same as the scallop height here. From the very valley of the cut to the very peak of the cut is identical. And what that means is that when your finishing tool is driving across this surface, it's going to see the same amount of loading and unloading as when it's driving across this surface here. And so you don't get a difference in the surface finish based on the precondition from finishing. It's really, really a powerful functionality. And iMachining 3D does this automatically for you. You don't have to even think about it. You just tell it what the scallop height is when you go in here to the operation. The technology wizard is where you can set the different levels, how aggressive you want to get. And that's going to be controlling, and we got two views down here, but that's going to control your spindle speed, feed rate. This is showing your radial step over. Whereas in view 2, we're showing velocity, chip thickness, and minimum and maximum angles, okay? And all of those are being adjusted simultaneously by simply moving the wizard to a different level. Makes it very, very easy for you to set up and get it going. Now, in the technology page, we have the ability here to assign, as you can see, a 10,000 scallop with a 10% tolerance on it, leaving a 10,000 stock on the wall. So the tool is only going to see a variance in the amount of material that it's cutting from 10 to 20 thousandths. And in most cases, a finishing tool can handle that when it's under the proper feeds and speeds and load, and therefore you're not going to get in and out flexing that's going to affect in a negative manner your surface finish on that part. And again, this part here that we saw today, we're running a finishing tool on it at 16,000 RPM and 160 inches a minute, and we're generating a 16 to 20 RA finish. It's pretty crazy, okay? All righty. Well, that's what I've got to show today. At this point, we can probably, we're going a little bit long, but we could probably sustain just a little bit more if we wanted to open it up for question and answer. So in that chat area or the questions box, if you have any questions, now is the time to start typing them in, and we can actually unmute you if you want to talk about something. So throw out any questions that you might have at this point, and we'll be happy to answer them.
Yeah, Ken, I've been monitoring the questions pane all throughout the presentation, and there are just a couple of comments from Lenny. Lenny would actually like you to come visit him at ASU Tempe, but other than that, I don't see a lot of questions in that. In fact, there aren't any other questions in the pane. So.
Okay, I see a little something coming in from Dave. He says pretty impressive stuff. Well, thank you, Dave. I appreciate that.
Absolutely.
Appreciate your time coming in today to watch it.
Excellent. And Dave, just again as a reminder, if you have any other further questions, just give our number a call. And one of the things that I really do want to get across as well, and Ken is tremendous at doing this, and Darren is as well, is that we consider ourselves solutions providers. We're not pushy about about trying to push you into a particular piece of software or a particular solution. Really what we try to do is we try to look at your particular workflow and then make a recommendation based upon that. And if it's a good fit for your company, great. And if it's not, well, that's okay too. It's just it's nice to expose you to the technology that's out there, and we're happy to provide that for you. So please do take advantage of the support team. So.
Well, if
Looks
there's
like
no other
that.
questions, then I think you probably ought to say goodbye and let everybody get back to work.
Absolutely. Well, Ken, fantastic job as usual, and thanks again for taking the time with me today. And again, to everybody on the panel, thanks so much. We'll see you next time around.
All
Take
right,
care.
guys. Everybody have a great day.